Today we are looking at the paper Forward Mode Automatic Differentiation for the Tensor Renormalization Group and its relation to the impurity method by Yuto Sugimoto. This research tackles a really massive bottleneck in computational physics. We're talking about calculating things like internal energy and specific heat in many body systems without, just running out of memory. The core issue is that while tensor renormalization group, or TRG, is great for finding the partition function, getting the derivatives of that function is a total nightmare. Numerical differentiation is unstable, and reverse mode automatic differentiation, the backprop we all know from machine learning, is just a memory hog. It scales with the depth of the computational graph. So Sugimoto proposes a forward mode AD framework. Instead of a backward pass, it propagates derivative info right alongside the renormalization flow. And the result: memory costs stay constant, totally independent of system size, and it gets way, way higher accuracy than the conventional impurity method. In fact, the paper proves the impurity method is actually just a stripped-down version of forward mode AD, where you basically ignore the derivatives of the SVD. It really unifies these two methods into one clean theory.
It really is. It's such a clean solution to a problem that's, it's been plaguing the field for a very long time. It's one of those papers that makes you go, oh, of course. That's how it should be done.
So let's back up for a second to just set the scene. We're talking about tensor renormalization group, TRG. For our listeners who might use PyTorch or JAX but haven't dabbled in statistical mechanics, what's the mission here? What are we trying to calculate?
The mission is to solve the many-body problem on a lattice. So imagine a grid of atoms, like a giant sheet of magnetic material. You want to understand its thermodynamics. And to do that, you need to calculate the partition function, usually written as Z. Z is, it's basically the sum of all possible states the system can be in, weighted by their probability.
And if you have Z, you have everything.
In theory, yes. Z is kind of the holy grail. But here's catchy: Z is just a number. It's a static value. To understand the physics, how the system changes, where phase transitions are, its heat capacity, you don't just need Z. You need to know how Z responds when you tweak parameters, like temperature.
You need the derivatives.
Exactly. The first derivative of the partition function gives you internal energy. The second derivative gives you the specific heat. And getting those derivatives accurately is surprisingly difficult.
Why is it so hard? I mean, in Calculus 101, derivatives are pretty straightforward. Can't you just calculate Z at temperature T, then at T plus a tiny bit, and see what the difference is?
You can. That's called numerical differentiation, or finite differences. But it's a blunt instrument. If your step size is too big, you miss the nuance. If it's too small, you run into floating point rounding errors. It's just numerically unstable. You get noise, not physics.
Okay, so finite differences are out. What about this impurity method? I've seen that term around. It sounds like we're dirtying up the sample or something.
It's not quite that dramatic. In a standard tensor network simulation, you have this uniform grid of tensors. Everything looks the same. The impurity method involves inserting one special tensor, the impurity, into that grid to act as a probe. It represents the observable you want to measure, like local energy.
So it's like sticking a thermometer into the grid.
Precisely. And for years, that's been the go-to method. It gives smoother data than finite differences, for sure. But, as Sugimoto's paper points out, it has a systematic flaw. It introduces a bias that, it limits your accuracy no matter how much compute you throw at it.
And we'll get to that flaw in a minute because it's a really cool reveal. But first, the elephant in the room. We're in the golden age of AI. Deep learning is built on calculating derivatives with backpropagation or reverse mode automatic differentiation. Why can't physicists just use that?
It's a totally valid question. And if you're training a neural net, backprop is king. But there's a structural difference. In deep learning, you have millions of parameters, maybe, but the computational graph, the layers, is relatively shallow.
Right.
TRG is different. It's iterative. You take a massive lattice of tensors and you coarse grain it. You combine neighbors, then approximate those blocks to keep the size manageable. You do this over and over again, zooming out logarithmically.
Like compressing a JPEG layer by layer.
Kind of, yeah. Now, to do reverse mode AD, to go backwards to find the gradient, you have to store the state of the network at every single one of those forward steps. You need the full tape or history of the computation.
Oh, I see where this is going. Since the number of steps grows with system size.
The memory footprint scales with the depth of the graph, which is O of log V, where V is the volume. And that might sound small, but in tensor networks, the things you're storing aren't single numbers. They are massive, high-dimensional arrays.
So if you try to store that history tape for a big 3D system, you just run out of RAM.
Instantly.
Yeah.
You hit the memory wall. For large-scale statistical mechanics, reverse mode AD is a complete memory hog. It's just not practical for the bond dimensions we need to see real physics.
So Sugimoto comes in and says, stop looking backward.
Look forward. Forward mode AD. That's the solution.
Walk us through the mechanics. How does it actually work?
It's surprisingly elegant. Instead of finishing the whole calculation and then rewinding the tape, you compute the derivative simultaneously with the tensor itself. So imagine you're carrying a piece of luggage. You have your main tensor, call it T. Right next to it, you carry a companion tensor, T dot, which represents its derivative. Every time you perform an operation on T-like, contracting it with a neighbor, you apply the chain rule right there on the spot to update T dot.
So you're keeping a running tally of the changes as you go.
Exactly. And here's the killer feature. Because you process it step by step, you don't need to store the history. Once you move to the next coarse graining scale, you could just throw away the tensors from the previous step.
And that solves the memory bottleneck.
Completely.
Yeah.
The memory cost becomes constant. It is totally independent of the system size. It doesn't matter if your system has 1,000 atoms or 1 billion atoms, the memory footprint for the derivative is fixed.
That is huge. But I have to play devil's advocate here. There's no free lunch in computing. If you're carrying this extra luggage tensor around, surely it slows you down.
It does. The paper's very upfront about this. You're doing more matrix multiplications.
Aye.
For the first derivative, the computational cost is roughly 3 times that of a standard run without any derivatives.
3 times. And for the second derivative, for specific heat.
That's about 6 times.
Wait, 6 times slower? That sounds expensive. In high-performance computing, burning 6 times more CPU hours is a pretty big ask, isn't it?
It depends on what you're optimizing for. In this field, the bottleneck is almost always memory, not time. You can wait 6 times longer. Maybe your simulation takes a day instead of 4 hours. That's annoying, but it's manageable. You cannot, however, download more RAM than what exists on your node.
Ah, I see. You can trade time for space, but you can't trade space for time if you just can't fit the problem in memory to begin with.
Exactly. If you hit that memory wall, you're just dead. Forward mode AD lets you climb over that wall. It makes calculations possible that just weren't before on standard hardware.
Okay, that makes perfect sense. Now, I want to get into the weeds a bit. There's a technical detail in the paper about differentiating the singular value decomposition, the SVD. Why is that part so tricky?
Right. This is where the math gets spicy. In TRG, coarse graining isn't just summing things up. You're finding the best low-rank approximation of a tensor to compress information. That involves calculating projectors. Let's call them E and F using SVD.
And since the tensor depends on temperature, those projectors must depend on temperature too.
Exactly. So when you apply the chain rule, you have to differentiate the SVD itself. You need to know how the singular vectors change when the matrix changes.
And I'm guessing standard libraries don't always handle that well.
They struggle, mostly because of degenerate singular values. If 2 data channels in your tensor are equally important, they have the same singular value, the derivative term has a denominator that goes to 0. It just blows up.
It goes to infinity.
Yep. The computer spits out not a number, and your simulation crashes.
So how does Sugimoto fix this?
He uses a technique called Lorentzian broadening. Basically, he introduces a tiny regularization parameter, eta. It just smooths out that divergence. It replaces the sharp divide by 0 cliff with a steep but finite hill.
So it keeps the math stable.
Exactly. It lets the simulation glide over those dangerous points without crashing.
This leads us perfectly to what I think is the biggest aha moment of the paper, the connection between this fancy forward mode AD and the old school impurity method.
Oh yeah, this is a beautiful piece of theoretical work. Sugimoto shows that the impurity method isn't just some different technique. It is actually a special case of forward mode AD.
But a broken one.
In a sense, yes. The paper proves that if you run the full forward mode AD equations, but you manually force the derivatives of the projectors to be 0, so you set E dot to 0 and F dot to 0, you mathematically recover the exact impurity method update rule.
Okay, I want to make sure I really get the implication here. Setting the projector derivatives to 0. What does that mean physically?
Think of the projectors as a lens. When you run TRG, you're looking at your system through a lens that compresses the information. The impurity method assumes that while the object you were looking at, the tensor, changes with temperature, the lens itself stays fixed.
But in reality, if I change the temperature, the best way to compress the information also changes.
Exactly. The lens should adapt. At high temperatures, certain correlations matter. At low temperatures, different ones do. Forward mode AD actually calculates how that lens shifts and reshapes. The impurity method just keeps the lens rigid.
So the impurity method is like trying to watch a moving object with a camera that refuses to refocus.
That is a perfect analogy. And because that lens is slightly out of focus, you get a systematic error. No matter how precise your math is otherwise, if your compression scheme is rigid, you're introducing a bias.
And the paper ties this back to that eta parameter we just talked about.
Right. The impurity method corresponds to the limit where eta goes to infinity. It effectively washes out the contribution from that changing lens. This proves that the impurity method is a theoretical lower bound on accuracy. You can never beat forward mode AD with it, because AD includes all the terms that impurity just ignores.
So let's talk numbers. They ran benchmarks on the 2D classical Ising model. How much better is better?
It's not just better, it's in a completely different league. For the internal energy, forward mode AD got error rates effectively at machine precision. We're talking errors of 10 to the minus 11.
And the impurity method?
Orders of magnitude worse. But the real shocker was the specific heat, the second derivative.
That's usually harder to get right. You're taking a derivative of a derivative.
Correct. The impurity method had relative errors of about 10 to the minus 1. That's a 10% error. In precision physics, a 10% error is, well, it's not great. It gives you a rough idea, but you can't make strong predictions.
And forward mode AD?
Errors smaller than 10 to the minus 5 near the critical temperature. That is a 10,000-fold improvement in accuracy.
Wow. Just by acknowledging that the lens needs to refocus.
And remember, the cost is roughly comparable. Yes, AD is 6 times slower, but the impurity method also requires complex contractions. In the grand scheme of things, you're getting vastly better accuracy for a very reasonable price.
One of the coolest applications they showed was calculating critical exponents. For our listeners who might not be deep in StatMech, can you briefly explain why we care about these?
Critical exponents are like the fingerprints of the universe. They describe how a system behaves right at the tipping point of a phase transition, like water turning to steam, or a magnet losing its magnetism.
And they are universal numbers, right?
Yes. They don't depend on the material details, just the dimensions and symmetry. If your code can reproduce the correct critical exponents, it means your simulation is capturing the fundamental physics correctly.
And usually extracting these numbers is a real pain. You have to do these scaling collapse analyses.
Yeah, it involves a lot of curve fitting. You plot data points, you try to fit a line. There's a lot of guesswork involved. It's an art form, and not always a pretty one.
Because forward mode AD gives them exact derivatives, Sujimoto could do something different.
Right. They calculated something called the Go-When ratio.
What's that exactly?
It's a quantity that measures the degeneracy of the ground state. You can think of it as a very sensitive thermometer for the system's order. And because they had AD, they could calculate the derivative of this ratio with respect to temperature directly.
So instead of plotting points and hoping for a straight line, they just asked the computer for the slope.
Exactly. They plotted the log of that slope against the system size. The result was just stunning. For the 2D Ising model, they extracted a critical exponent of 1.000053.
And the theoretical exact value is 1.
It is exactly 1. So they are accurate to within 5 decimal places.
Yeah.
That just blows the old scaling collapse methods out of the water. It turns a guessing game into a precision measurement.
That is incredible. But the paper didn't stop at 2D. They tried to take this to the 3D Ising model. And that's where things got a little complicated.
3D is always the final boss in tensor networks. The complexity just explodes. In 2D, you contract squares. In 3D, you're contracting cubes.
They mentioned they could extract the exponent, getting about 0.57, but the known value is around 0.63. Why the gap?
It really comes down to bond dimension, what we call D. This is how much data we keep during compression. In 2D, they could push D up to 130. In 3D, due to memory and time, they were stuck at D equals 32.
That's just not enough resolution to capture the complex 3D correlations.
Exactly. But they also ran into a specific instability with the SVD in 3D that I think is really important. It goes back to those degenerate singular values.
The ties in importance.
Right. In 3D, because of the high symmetry of the cubic lattice, you get a lot of singular values. They're exactly equal. If your truncation cutoff D lands right in the middle of a tie, say, values 32 and 33 are identical, you have to make a choice.
You keep one and throw the other away.
You make an arbitrary choice, and that choice breaks the symmetry. And worse, as you change the temperature slightly, that tie might break or swap, suddenly your projector jumps.
And if the projector jumps, the derivative goes infinite.
It causes these non-physical spikes in the specific heat calculation. The paper shows these jagged peaks that just shouldn't be there. They suggest adding a tiny external field to break the symmetry on purpose, which smooths it out, but then you aren't strictly simulating the pure Ising model anymore.
This leads to a fascinating philosophical point the paper raises at the very end about gauge freedom.
Yes, this is a profound warning for the whole field, I think.
It's this idea that within those ties, there's an arbitrary choice of gauge. If our numerical truncation depends on an arbitrary choice inside the math, are we even simulating real physics?
It really raises a red flag. If you don't explicitly protect your symmetries, if you just let the computer choose how to break those ties, you might flow to the wrong fixed point. You might be simulating a universe that doesn't actually exist.
It's a reminder that numerical methods aren't just number crunching, they're physics. If you truncate the math, you might be truncating reality.
And forward mode AD is like a high-powered flashlight. It shines such a bright light on the calculation that it reveals these tiny cracks in our methods, like that gauge ambiguity that the impurity method used to just fuzz over and hide.
So the smoothness of the impurity method was a lie.
Essentially, yes. It was a comfortable illusion.
So bringing it all together, we have a method that offers constant memory scaling, a massive win. It unifies the field by showing the impurity method is just a low accuracy approximation, and it delivers machine precision derivatives. What's the final verdict?
If you are writing tensor network code today, you should probably stop looking backward. Forward mode AD is the robust, rigorous way to do thermodynamics. The memory savings alone make it the clear winner for any large system.
And maybe we need to buy a little more RAM for those 3D calculations while we're at it?
Couldn't hurt. And, work on those symmetry blocking techniques to handle the degeneracy better.
There's always more work to be done. This has been a really fascinating deep dive into the machinery of computational physics. It's rare to see a paper that so cleanly retires an old method and replaces it with something just so much better.
It's a great contribution by Sugimoto. Definitely a paper worth reading very closely.
Absolutely. Thanks for joining us for this deep dive. We'll catch you on the next one.